Now, question number 7 and question number 8 are about chapter 7. It's quite visible from the structure of the questions that you have moved from one domain of thought to another field of understanding. You do have only one capacitor. No more capacitor, no more inductors. First degree you can identify. This is in time domain and it's DC. You have a function of u of t, of course that's one thing, and then you have a switch. All of these are indications that you are in a time domain analysis, you are in DC analysis, you are trying to capture both transient as well as a steady state response, and there is a famous formula that you need to remember by heart. For a first degree design, differential equation, such as the one that applies to this one, you're going to have y of t as equal to y of infinity plus y of 0 plus minus y of infinity e to the power of minus t over tau. Looking at this famous equation, it tells you need to find 3 prominent terms to be able to write this. You need to tell me how much y0 plus is. You need to tell me how much y of infinity is. This, and then you need to tell me how much tau is. If I have these 3 unknowns, then I have my equations. And I don't have to write the differential equations that are going to be costly in terms of time. Of course, as a person who has interest in deep understanding of the events, I do encourage you, and eventually you're going to be forced to know how to write a second degree, third degree differential equations, mechanical, aerospace, everybody in the 3rd year, 4th year, you are going to be forced to write them. But at this time, you don't have to. So I need to have y of 0 plus, y of infinity, and tau. And for each one of them, we had algorithms, steps, outlined in YouTube, on Blackboard, inside the classroom. So everybody should know what to do with that. Okay. What was the step? The step is this. Regardless of what it is, give me the 2 topologies, before and after the switching event. Where are my switchings? This one, the door is open, and someone comes in with the pressure of a hand. This is my hinge, this is the hinge. With the pressure of a hand, it tries to close the door. So the door is open, and then it goes and closes horizontally. That's what happens. Initially, it's open, okay? U of minus t. What is u of minus t? We had an understanding in regard to what u of t is. U of t was a nice function. This u of t, shape-wise, graph-wise, supposed to be 0, goes up, and then flat response at the value of 1. But mathematically, u of t was supposed to be understood in the following way. I emphasize that u of t, you need to see inside the bracket, whatever inside the bracket is. And inside the bracket, if it is less than 0, you get me a 0. If it is more than 0, you get me a 1. Inside this bracket, whatever it is. For example, if I say u of, let's apply it on this one. When I say u of minus t, what do I mean? I mean inside the bracket is less than 0 is 0, inside the bracket is more than 0 is 1. This bracket is going to have a decisive outcome as to how the shape is going to be. And that's going to help me to understand the value before the switching event and after the switching event. Minus t less than 0. Take this to the other end. What do you get? You get t greater than 0. Minus t greater than 0. Take this to the other end. Is going to be less than 0. For t greater than 0, you got yourself 0. Let's translate that into basically the curve. For t greater than 0, you got yourself 0. For t greater than 0, you got yourself 0. For t less than 0, you got yourself 1. That's the way I'm going to see u of minus t. Okay? So my focus will be inside the bracket, this one. Now, what are my critical points in the process? I have a u of minus t where the switching happens at 0. I have a switch where the switching happens at 0, so 0 is my only switching event. I need to have the two topology before and after the switching event. This is going to be a resistor, this is going to be a capacitor. The capacitor is this one, 0.2 farad. The switch is open, I'm going to leave it open. The switch is going to be open, that's going to be 10. That's going to be 3 amp. Okay. And then I need to see how much this is and represent this. That's one. The second thing is going to be, again, the capacitor, 0.2 farad, and then the switch is now closed. And then you have 10, and then you have 3 amp, and then you are in. And I need to know how much this voltage is. Let me duplicate the value, 5, 10, 10, 3 amp, everything is fine. Okay. I took care of this switch. How about this guy? For t, this is supposed to be t less than 0, and this is supposed to be t greater than or equal to 0. The switching event is 0. The moment that topology actually changes. Now, for t less than 0, u of minus t is 1. 1 times 20, you've got yourself 20. So this is 20 volt. For t greater than 0, u of minus t is 0. 0 times 20, that's going to be 0 volt. And 0 volt, we know, is going to be a short line. So basically, I'm going to replace this with a short line. So what did I do? 2 of u of minus 20 times u of minus t. I calculated it. If it is 0, I'm going to actually replace it with a short line. So far, so good. The next thing I like to do is to see what the variable of interest is. The variable of interest is this voltage and this current. This current and this voltage. The reason I need to know what the variable of interest is in this case, you can see a broken circuit. You can see there is a partial of a design that's working on the right hand side. You can see a partial of a design that is working on the left hand side. But you see a broken line. Because it's a broken line, there is no current that goes in. If there is no current goes in, what happens to this line? If I claim that the current is coming this way, when it comes in, it never leaves. Comes in, never leaves. This part is going to be unstable. This has no current to have a stable response. And if that's the scenario, I can actually remove it. Now, you want this voltage. You want this current, whatever it is. You want the capacitor. Even this current really doesn't matter. You want the capacitor because capacitor is the main point of attention. You want to find the voltage of the capacitor. Regardless of whether it's the I of a resistor or not, you want to find the voltage of the capacitor because that's the only voltage that is going to remain the same from 0 minus to 0 plus. Momentarily, it's going to be the same because it's resistive. Of course, a note of caution, and doesn't apply to this class, and that is when you have multiple capacitors, things could happen at that 0 minus 0 plus, even for the capacitor, and we are not interested in that part at the moment. Lots of mystery if you want to come and join us in electrical engineering. There are lots of mystery that you will see and enjoy if you come in. Okay. I needed to draw two topology, this and this. I needed to see where the capacitor is. That's what the capacitor is. And since this is broken, since this is working by itself, since this is not interacting with this one, I'm actually going to remove this. It doesn't do anything with this part. Okay? Let's go and see what happens. regardless of the variable of interest, whether it's the voltage of a capacitor or not, the current of a capacitor, the current of a resistor or not, I need to find this current, this voltage, the voltage of the capacitor, because it's going to remain the same as it transfers from one topology to the next. Momentarily, it's going to remain the same. So I want to know how much this voltage is. Okay, let's begin translating the keywords of this process. The switch was open for a long time and then closes and remains for a long time. The long time is the keyword, and it has been done twice. The switch was open for a long time, and then the switch closes for a long time. Let's take a look at each topology one at a time and try to understand the voltages. This topology has been there for a long time. This is a DC incoming signal. Okay? Now, as I said, if you let it go for a long time, the capacitor is going to act like an open line. If the capacitor acts like an open line, I refer you to the YouTube recordings we had previously. This is going to be open, the current is going to be 0, this current is going to be 0, this voltage is going to be 0. So basically this 20 volts, if you write the KVL law, is going to dump itself across the capacitor. I'm going to say VC of 0 minus is equal to 20 volts. And that's only for one moment in time. VC of 0 minus is 20 volts. Because the system is a combination of capacitors and resistors, I'm going to claim that CVC of 0 plus is going to be the same as VC of 0 minus is the same as 20 volts. I found the variable of interest, in this case, voltage of a capacitor for 0 plus. I need to find VC of infinity. In order to find VC of infinity, I'm in the 0 plus mode. My T is more than 0 plus now. And I'm going to let this design go for a long time. When I let it go for a long time, the capacitor is going to act like an open line once more. The idea is, how much is this voltage? That's going to be my VC of infinity. How much is this voltage? Well, it's not really difficult to see how it's done. You have a 10 ohm, you have a 5 ohm. If you take this and play a yo-yo like we did in the first place, 5 and 10, they are going to be in parallel. And the outcome is going to be in parallel with 3 amp. So you've got yourself a 3 amp times 5 ohm in parallel with 10 ohm. You need to see this now, as we expect you to be in a very mature state of analysis. 5 and 10. Now, for 2 resistors, we can say 5 times 10 divided by 5 plus 10. So that's going to be 50. 3 times 50 divided by 15. That's going to be 5. That's going to be 10 volts. If you let it go for a long time, the capacitor is going to act like an open line. 5 ohm and 10 ohm would be in parallel. The current comes in, hits on top of the parallel resistor, and creates a plus on top and a minus at the bottom. So in terms of polarity, I'm fine. I'm double checking everything. The last thing I need to find is to find the tau. I need to stand across the capacitor. This is the capacitor. I need you to put 2 feet across the capacitor and basically take a look at the design. Shut down all independent source to 0. So you have an independent source of 3 amp, shut it down to 0. Okay. And tell me how much resistor do you see? Why do I need that? Because my tau, and this tau is independent of the variable of interest. Whether it's a current or the voltage or so, it really doesn't matter. This tau is the same for every other variables in this first degree design. Tau is equal to R equivalent times C equivalent. C equivalent, we already know, it's 0.2 farad. But how much is R equivalent? If I pick up the two nodes A and B, or the top and bottom of the capacitor, and take it out, and simply shake it in front of yourself, you can see 5 and 10 would be in parallel. 5 and 10 in parallel, we already know, it's 50 divided by 15. Okay, so that's going to give me 0.1, that's 5 times 2, that's going to be 10, am I right? 0.2 is 10. 10 divided by 15, that's going to be 2/3 of a second. It's going to be 0.66 of a second, almost. You are now ready to tell me this is what it's going to be. Let me go back to my original design. You had a capacitor. You were looking for the voltage of the capacitor, the polarity. You had a current source, and the current source, I believe, was 3 amp. Okay. You let this to go for a long time, and you found VC of infinity. You know what VC of 0 minus is. You know what tau is. You can tell me how this function is for 0 plus onward. So I'm going to say VC of t, and I'm going to say for t greater than or equal to 0 is equal to VC of infinity, 10. VC of 0 plus 20. VC of infinity, 10. E to the power of minus t divided by tau, which is 2/3. This is your function. Now in some textbooks, they take this into account. When you say t greater than or equal to 0, you are specifically demanding the voltage to be represented for t greater than 0. So in some textbooks, they say this is 10 plus 20 minus 10, e to the power of minus t divided by 2/3. And then they say, okay, you said 10 greater than t greater than 0, right? With y of t, I'm forcing the value to be 0 before. You don't have to do it now, though. This is only for that stage. For before, of course, you have something else to worry about, right? So if you want to take this into account, you can actually force it by u of t, but we don't want you to worry at it at this time. Let's get rid of this for now. We are going to say this is the response for t greater than or equal to 0. As simple as that. Well, the design is asking you to find this current as well. One of the things I mentioned in one of the sessions I had, both in class and the YouTube, is that no matter what the variable of interest is, always go find the VC all the way to the infinity, give me the function for VC. Give me the function for VC, and then come back and simply replace the capacitor with a voltage source of the given function you just found on top. So here is my design, and the question is, how much is I in time domain for t greater than 0? I can actually remove this. I'm going to apply a plus minus voltage source, and the value is going to be, I'm looking at that, 10 plus 10 e to the power of minus t divided by 2/3. It's a voltage source. Capacitor is a voltage source. Its value happens to be a non-DC value. It's an exponential function, and that's my system. Now, if I'm asking you to find I, okay, take a look at this 5 and bring it in front of this voltage source. Now, I'm asking you to find I this way, but this voltage is dumping itself across the 5, and since this is plus and this is minus, the current is going to go this way. Because I'm asking opposite value of the current provided by the Ohm law, then I is equal to, because I said opposite value, if I is this way, Ohm says this way, right? It's going to be equal to minus 10 plus 10 e to the power of minus t divided by 2/3 divided by 5. Done. It's minus 2 plus 2 e to the power of minus t over 2/3. Let's go for question number 8. In question number 8, we always provide you with one question on RC and one question on RL. Let's go for RL scenario. Okay. In RL, you can do the same thing as we did for the capacitor, except that you focus on the current of the inductor. And when you are done everything with the current of the inductor, you can always replace the current of the inductor itself, with the current source of the value of the function you just found. If you have a current source, then you can go and find any other variable of interest that you have inside the design. Okay. Okay, this one is going to be 12 amp, 30 ohm, a switch. The switch seems to be closing at t is equal to 0. 6 ohm, 5 ohm inductor. Inductor is 2 Henry, and then a current source 2 amp. The variable of interest is IT, which is the I of the inductor. Let's sit back and make sure you copied this correctly. Yeah, everything is fine. So, do you have a U of t? If you do, you have to take care of that too. Do you have switch 1, switch 2, switch 3? If you do, for every switching moment, you have a before and you have an after. So if you have 2 switches at 2 different times, you're going to have 3 different topologies. If you have 10 switches, you're going to have 11 topologies. So in this case, you have 1 switch, very simple one, and the switch is open and then it closes. So give me before and give me after. Before, I'm going to have the 12 amp, I'm going to have 30, I'm going to have an open line because the switch is open before the switching event. I'm going to have 5. I have an inductor, 2 Henry. I have a current source, 2 amp. Don't rush to make any judgment. Just simply go ahead and draw the 2 topologies before and after. Now the switch is going to close, 12 amp, 30. Oops. The switch is closed. 6, 5, inductor, and the current source. Make sure you copy this properly and you don't make a mistake just by copying it. So that's what it is. This is an inductive design. It's a first degree design. The input excitation is DC. You are in chapter 7. So therefore, I'm going to focus on the current of the inductor. I might have asked you to find something else, but I'm going to ask you to focus on the current of the inductor, this current. And it seems to be the same as the variable of interest. That's the first thing. The second thing is this. This is a broken line. Therefore, this has to be 0. And therefore, this section, although functional, is not interacting with this one. I don't have a dependent source. I have everything independent. I might have a dependent source, 1U, that may have a relationship with the left-hand side. We don't have it at the moment, and therefore this one is going to be removed. That's what this is. What can I do? I want to find IL of 0 plus, I want to find IL of infinity, and I want to find tau of L, T. So I need to find IL of 0 minus, safely transfer it to IL of 0 plus, and then continue observing its behavior until infinity, and then get the tau L, and I'm done. This one, the system is there. For a long time, an inductor is going to act like a short line. We discussed that a long time ago. If this is a short line, I want to replace this with a short line. This is 0, 5 and 6 is 11, fine, but 0 divided by 11, this is voltage-wise 0. Voltage-wise 0 and 11 in front in parallel, 0 divided by 11, that's a 0 current that goes in. Therefore, this one doesn't have any current. The 2 amp comes in and it goes this way. The 2 amp come in and they see resistive path and least resistive path. They pick up the least resistive path. In this case, 0 resistive path. And therefore, IL of 0 minus is going to be minus 2 amp. I hope I had the directions of the current source correctly. Okay. It's coming in. All the current go through this short line. All the current come in and oppose the direction I assigned. And therefore, IL of 0 minus is 2 amp. I'm done with this. I'm going to take this off and then go and focus on the after the switching event. It's going to be IL of 0 plus as equal to IL of 0 minus. The current of the inductor remains the same when it goes from one to another. So it's going to be minus 2 amp. Take a look at this design now. This is the T greater than 0. You have one inductor, everything is DC. Of course you can apply the concept we discussed, and that is, if you leave this for a long time, the inductor is going to act like a short line. This is going to act like a short line. I'm talking about infinity now. This one is IL of infinity. I want to find this. Well, there are many ways you can handle this. You can actually do shrinking on this part, because this part is really nothing. There is nothing of interest in this at the moment. I can shrink this and let's see what happens. 30 and 6. Oh, these are, did I copy correctly? Yeah. 30 and 6, they are in parallel. And what happens? I can actually replace it with one resistor. 30 times 6 divided by 30 plus 6. So I can replace these two resistors. Because they are in parallel and there is nothing of interest I want, I can shrink this. And let me go and calculate this. 30 times 6 divided by 36. It's 5. This is equal to 5 ohm. Okay. I have 12 amp and I have 5 ohm. I can actually do a source transformation. That's a building block I'm familiar with. I'm just trying to reduce the complexity of the design. Because that part is complex and it has nothing to do with the point of interest, I'm actually doing a kind of a compression, secant reduction. But of course, if there is anything of interest, I can always do decompression. And I can come back and get that back in. 12 and 5, I can replace it with a voltage source and a resistor. How much is a resistor? If this is 5, this is going to be 5. If this is 12, 12 comes in, hits on top of the 5, so it's going to create a plus and minus in terms of polarity. 12 times 5, that's going to be 60 volts. Okay, so I'm going to remove this. I'm going to remove this. And I have this. 5 and 5, 10. Let's shrink this. This 5 and 5, that's going to be 10. Still, the point of attention is the eye of that short line. I can do one more source transformation if I want to. So that's one of the techniques though. You can do nodal, you can do mesh. We might as well do mesh sometime. So 60 and 10, I want to change that in terms of source transformation. It's going to be a current source and it's going to be a resistor. The value of resistor is going to be 10. 60 divided by 10, that's going to be 6. The direction, if I have a virtual short at the end of 10 ohm, I have the current to go this way, and then I have to have the current to go this way. So that's the direction as well. Okay, let's safely remove this. And now you're ready to tell me what is happening. Okay, you have a short line. This short line is in parallel with the 10 ohm. The short line has a 0 voltage. 0 voltage divided by 10, that's a 0 amp. There is no current that goes in. People, 6 amp on this side and 2 amp on this side. You can actually, these are all in parallel. You can actually combine these 2 and 6 and see what happens. So let's combine this. Because they see head to head and toe to toe, I'm going to have one current source. If I stand on this node, 6 amp come in, 2 amp leave, it's going to be 4 amp. So 6 amp is going up, 2 amp is leaving, 6 minus 2, that's 4 amp. And then you have a 10 ohm, which is doing nothing. And then you have a short line. And this short line is the variable of interest you want to find, this one. Now you can see that this current come in, and they see a resistor of 10 ohm, and they see the 0 resistive pass. And obviously all the 4 amp go in. So IL of infinity is going to be 4 amp. You can also benefit from this reduction you did. Remember, you replaced the inductor with a short line. So this was originally an inductor. Originally, this was an inductor of the value of 2 Henry. I want to find tau L. Tau L is L divided by R. And I want you to go across the inductor, put your feet across the inductor, shut down all the independent source that you have, and tell me how much resistor do you see. That's 10 ohm. Don't dismiss this 10 ohm too fast, because obviously at this stage it's going to be very helpful. 2 Henry and then 10 ohm. This is going to be 0.5 seconds. The unit is seconds. Okay, you're ready.
0.2.
0.2, yes, 0.2. Thank you very much. 0.2 seconds. So you are ready now to tell me for this domain how much I of LT is. I of LT is going to be infinity, 0 plus, infinity, e to the power of minus t over tau. So this one is going to be 4 minus 6 e to the power of minus t over tau. Okay? Now suppose that I want you to find me, I'm just making a case, this voltage. All you have to do is this. After the switch is going to close, I'm going to have this as, you see the switch was open and then it's going to close. So that's what the t greater than 0 topology looks like. Now that you have gone through so much trouble to find this, all you have to do is to actually replace this one with a current source. The current source, the direction, you maintain the same direction you had in the original circuit assigned, and the value of this current source is 4 minus 6 e to the power of minus t over tau. If you do that, you have a current source, you have this, they are in parallel, you shrink it, you do this, everything is resistive, you solve this. And when you solve this, you've got yourself V of 6 ohm. So what I'm saying is that, regardless of what the variable of interest is, focus on the voltage of the capacitor, focus on the current of the inductor, solve it all the way, and then come back and say, okay, I want to find this one, and see what happens. If you don't want to do that, again, take a look at the steps I outlined. You have to find VC0 minus. You have to find VC0 plus, which is the same as VC0 minus. You have to find IL of 0 minus. You have to find IL of 0 plus, which is the same as IL of 0 minus. You have to find them, and momentarily, then you have to replace them with the current source or the voltage source. So you have no choice. You need to get used to this idea as the fact that the current source, the capacitor acts like a voltage source, and inductor acts like a current source. I want to go in and solve the last question. The last question is about the power. In some exams, we have the AC power as the last question. In some exams, we have a simple DC power in the design. Okay. We have a 5 amp, 2 ohm, 160 microfarad, 4 millihenry, R, which is unknown, and then that's it. For the circuit, calculate the value of R that will make the energy stored in the capacitor the same as the stored in the inductor ion under DC steady state response. So I want the energy in this to be the same as this, and the system, excuse me, that's the smell of this one. I want this energy and this energy to be the same. I have a DC excitation. So what happens is that since this is DC, a capacitor is going to act like an open line. An inductor is going to act like a short line. So this one is going to act like a 160 microfarad. It's going to act like an open line. This one is going to act like a short line. I want to identify this using a red marker. So that's open. And this is going to be a short line. Okay. How much energy is stored in a capacitor if I know what the voltage is? The energy in a capacitor is 1 over 2 CV2. The energy inside an inductor is 1 over 2 Li2. Because I'm talking into time domain and I have DC excitation, I'm going to write a small letter v, a small letter I. I want these two to be the same. So this one and this one, you get rid of it. You have C and L, of course. How much is V though? V is this V. Agree? Because the capacitor is in parallel with the resistor, right? Now, take a look at this and tell me how much is my current. How much is my current? You see this one, this current comes in, this current comes in, this current comes in. The current that goes in is the same as the current, because this is open. This current and this current is the same. So if this is my I, this same I is actually applicable to the R. How much is my V then? Once again, C. The V is R, I, and then everything to the power of 2. That's the V across the R. How much is the I? I is the same, so it's going to be Li2. I don't have to solve this. Some people did. You don't have to solve this to find it. If you take it to the power of 2, it's going to be CR2, I2 as equal to Li2. I2 is gone, and therefore R2 is equal to L divided by C, and therefore R is equal to square root of LC. I have L, I have C, you put that in, let me put that in. So I need to be careful about milli and micro, so I'm going to open bracket 4 exponential, EXP, not exponential, EXP minus 3, because that's milli, divided by 160 EXP minus 6, because that's micro. Okay? And then when you do this, you need to, that's 25 actually. And then 25 Did I do it correctly? Yeah, makes sense. Okay. And then this is going to be a square root of 25. And if I take this, then it's going to be 5 ohm. Just double check my numbers because that's too nice to be true. Is that it is? Okay. So we started at 10, 20, 25. We took a bit of a break. Right now it's 1 p.m. and we solved our questions, and along with you I went through the calculation and the calculators, and I've got at least 20 minutes, 25 minutes extra to do the job. I did explanations, I did variations, I did everything, and I have so much time. If you exercise the same amount as I did, perhaps a bit here and there, then you should be able to have a lot of time on your hand to be able to successfully, happily finish this final exam. Thank you very much, and I'll see you later.